Hello, my name is Hugo Aramberri, and this presentation is about our recent works where we propose how to create currents of ferroelectric skyrmion bubbles and how these objects can serve as a testbed for chiral transitions in solid state. So I work at the Luxembourg Institute of Science and Technology, and all these works have been funded by the National Research Fund of Luxembourg. Now, the works I'll be presenting here are part of a bigger effort to study ferroelectrics in frustrated regimes where they can be very responsive. So here you can see some of the people with whom I've collaborated on such topics, and in respect to this presentation, all the works that I will be presenting have been carried out together with Jorge Íñiguez-González, who is the head of my group at LIST, and one of the works is the result of Urmimala Dey's postdoctoral stay at LIST with me. I always like to introduce the topic by first speaking about frustrated ferroelectrics. Now, picture your favorite ferroelectric, say for instance lead titanate, and imagine that you sandwich it between dielectric layers, like for instance strontium titanate. Now in this scenario, there is a competition that arises between the polar distortion in the ferroelectric layer and the electrostatic energy penalty imposed by the surrounding dielectric layers. Now, this competition often results in the ferroelectric breaking into domains of opposite polarization, so that in this way the polar distortion is developed, but this electrostatic energy penalty is minimized because if you count dipoles here, the net polarization is 0. Now, such domains are typically shaped as stripes, and this would be just a top view through the center of the PTO layer. Now, such dipole patterns were first predicted using first principle simulations over now a decade ago, in precisely lead titanate strontium titanate superlattices, and some 4 years later it was experimentally measured in those same superlattices. So this is the experimental verification, and this allows me very briefly to introduce the kind of methodology that I will be presenting, or I'll be using in the remaining of the talk, which is second principles calculations. So without going into details, let me just mention that this kind of methodology relies on writing down the energy of a given compound as a Taylor expansion around a reference structure. And we write this Taylor series as a function of atomic and strain degrees of freedom. Now, the coefficients of this series can be fitted to first principles data, and the resulting model can be made arbitrarily accurate by increasing the length or the order of this Taylor series. Now, the second principles models that we have developed, people in the group before me had developed for lead titanate strontium titanate superlattices, have been very largely used, and they have been very successful in many different works. So here I will just give you a list of the different scenarios where they have been applied successfully. So long story short, what we know is that these atomistic models are actually very good, not only qualitatively but also quantitatively. Now, this kind of frustrated ferroelectric state is very interesting for many reasons, and I will just name here a few of them. So these systems can be very responsive, so much that they can act as a negative capacitor and therefore locally amplify an applied voltage. They were also the first systems in which the electric skyrmions were first observed, and since then other topological textures of dipoles have also been seen in such systems. They can also act as artificial anti-ferroelectrics and even store very large energy densities. There are also proposals on how to manipulate the domain structure within them using light. And they even made it to the cover of Nature in this work, where they showed that there is a collective motion of essentially the centers of these vortices, which has very low frequency and can therefore be used for potentially telecommunication applications. All right, but I told you I will speak about bubbles, and you haven't heard anything about bubbles yet. So let's go to it, and let's hope that you see why I started speaking about frustrated ferroelectrics. All right, so imagine that we have our lead titanate strontium titanate system in this stripe domain state, and now imagine that we apply a field in the vertical direction, or in this case in the direction perpendicular to the screen. So we will favor the green domain over the pink domain, and initially what will happen is that precisely these green stripes will widen at the expense of the pink domains. But if we keep on increasing the field, eventually these infinite stripes will actually break into finite size objects or domains, so that their domain wall area is minimized, and therefore the domain wall energy is minimized. So here's just a simulation where we have prepared our favorite PTO-STO superlattice in this ground state at 0 Kelvin. We now apply a field and we allow the system to evolve. And what we see is that the stripe domains very quickly break apart, and what we are left with are these bubble domains. So just to be clear, the bubble domains are minority domains that live in a matrix of majority domain, and that essentially span typically the whole thickness of the ferroelectric layer. Now, bubble domains have been observed in many different ferroelectric dielectric systems, not only lead titanate, strontium titanate, like the one we were seeing before, but also in the closely related PZT-STO systems, but even in systems beyond lead zirconate or lead zirconate titanate, like for instance bismuth ferrite strontium titanate heterostructures, and I even found one report of such bubble domains in a bulk ferroelectric. Alright, so now we know how to prepare our lead titanate strontium titanate superlattices such that they will show bubble domains, and now let's see how they behave under different conditions. So for this we will use molecular dynamics, and here I want to give you a kind of a flavor of or a bit more of insight into the type of calculations that we run. So we run again atomistic calculations, and in these figures that you are seeing, every arrow that we are plotting corresponds to a local dipole computed from essentially a 5-atom perovskite unit cell. Now, the typical simulation boxes contain something around 16 by 16 perovskite unit cells in the plane, and one period of the superlattice along the vertical direction. Now, thicknesses of the lead titanate layer typically go from 3 to 12 perovskite unit cells, which overall means that we are simulating of the order of 15,000 atoms. Now, we always run simulations under periodic boundary conditions, and we run them for a few nanoseconds with a time step of half a femtosecond. Alright, so now I'll play for you a video of one of these molecular dynamic simulations, and in this case it will be at 150 Kelvin. So, well, we were super excited when we first saw this. You see that these two bubble domains in our simulation box start to move around stochastically while keeping essentially a roughly constant shape. So we found this super exciting, as you can imagine. Then, of course, we wanted to characterize this motion of the bubble domains. So let me quickly say here that what you will see now is a similar simulation where we have prepared the system in a way that only one bubble per simulation box will appear at room temperature. And what you're seeing here is only a cut through the center of the lead titanate layer. And to stress the fact that we are using periodic boundary conditions, here I am showing 4 copies of our simulation box. Alright, so in order to characterize their trajectory, what we do is as follows. So we fix a specific time window, and we see how far the bubble has moved in that time window, and we can run this time window all through our very long trajectory. And in this way, we start to gather statistics of the travel distance at the given time across the whole simulation. Now, the histograms look typically like what you see here on the top right. And the good thing is that we can repeat this process for different time windows. So from analyzing this data, we can now plot the average of this mean square displacement as a function of time. And what we see is that the mean square displacement of these bubbles is perfectly linear with time. Now, in case you're not familiar with this is precisely the defining feature of diffusive motion. So from this analysis alone, we arrive at I think the most important message from this talk, which is that electric bubbles behave as Brownian particles. Now, the diffusion coefficient is essentially given by the slope of this curve, and one thing we can do now is change the temperature and see how temperature affects the diffusive motion of these Brownian particles. So by doing this for several temperatures and then plotting them, the diffusion coefficients against the inverse temperature, we see that they follow very well, very beautifully, an Arrhenius law. So this second result means that this Brownian motion is actually thermally activated. So if you want to know about more details and also some interesting calculations that we did to try to compute interactions among bubbles, please check out this article that we published 2 years ago in PRL. Now next, we wanted to see if we could direct this stochastic motion in a way that we can create controlled bubble currents. And for this, we came up with two ideas that, as you will see, are very closely related. So the first one is what we can call the field gradient approach, and the idea is as follows. So I've told you that in order to stabilize the bubble domains in the simulations, we have to apply a constant electric field. Now imagine that now we superimpose on top of this homogeneous field a small inhomogeneous component that is linear along one direction in space. Let's call that direction x. So we know from our simulations that the bubbles will tend to move towards the regions where this field is smaller. So now what we have is essentially a system of diffusive particles in the presence of a constant force. And this is very nice because this is directly analogous to the problem of sedimentation of particles in water, which is great because this is a very well-studied problem. So in particular, we can use what's called the Smoluchowski's equation for sedimentation diffusion equilibrium and its analytical solution. And from the analytical solution, we see that the particles will show an exponentially decaying probability distribution, where the exponent precisely connects the drift velocity of these bubbles with the diffusion coefficient of the bubbles themselves. So now we can implement these field profiles in our code and start running molecular dynamics to acquire statistics of the positions of the bubbles, and we can start plotting probability distributions like you are seeing here below. So what we find is that the resulting histograms can be fitted very well with an exponential decay, at least when we move slightly away from the wall. Now, since we know how to compute the diffusion coefficient, we can essentially, from these fits, extract the bubble drift velocity. So we can also play with the amplitude of the inhomogeneous component, so the gradient of this field that we superimpose. And what we see is that when you increase the amplitude of this inhomogeneous field, the histograms become narrower and higher, and therefore what we get is a larger velocity. And we can even plot the drift velocity as a function of this amplitude of the inhomogeneous component. And what we see is that essentially you can increase basically linearly the speed of the bubbles by increasing the amplitude of this inhomogeneous component. Right, now let me show you our second idea, very related, as you will see, to move bubbles using inhomogeneous fields. So again, we start from this situation where we have a homogeneous field all over the place to stabilize the bubble state. And now we superimpose again an inhomogeneous field, but this time we will make it sinusoidal for simplicity. So again, we know that the bubbles will tend to move towards the regions where this field is minimal. And now what we will do is that we will move this sinusoidal field as time goes by, in this case towards the right. So we call this the stroller approach because the basic idea is that we put the bubble in a stroller, and now we start pushing the stroller with the hope that the bubbles will essentially follow this movement. Okay, so here I will show you some results from a molecular dynamics simulation using this idea. So we have only now one bubble per simulation box, but here you are seeing many periodic copies of it. And the vertical lines indicate the position of the electric field minima, and in particular, the purple line is the one that corresponds to the one that is closest to the initial position of the image of the bubble that we will be keeping track of. All right, so what we see is that this essentially works. When we run the simulation, we find that the bubble is essentially following this electric field minima position. And in this way, it is moving towards the right as we intended, so in the direction of the field pulses. And in the vertical direction, what we see is that the motion is still essentially Brownian. All right, so then of course, the next thing we wanted to see is how fast we could drive the bubbles using this idea. So we started to crank up the speed of these electric field pulses, and eventually we did reach a regime where these bubbles that you will see here on the screen can no longer keep track of these electric field pulses. So here when we drive the pulses very fast, what we see is that essentially the bubbles cannot keep track, cannot follow, although eventually they do catch one of these pulses or trains if you want. So every now and then it does get hit towards the right direction, but of course what you can imagine is that this process is much less efficient. So we can repeat these simulations for different speeds of field pulses as I showed you, and we do find that there is a maximum speed, and in this particular superlattice, this one that is composed of 6 layers of lead titanate, 3 of transium titanate, and then it's run at 200 Kelvin, what we find is that these bubbles cannot go faster than 100 meters per second, with an amplitude of the sinusoidal component of essentially 50 kilovolts per centimeter. Now, what we do find is that if we, again, increase the amplitude of the inhomogeneous component, we can make the bubbles go faster and faster. So we can kind of push this limit a bit further. Now, we can go to a more realistic scenario where, at least in our computer, the bubbles are stable at room temperature. And for that, we have to go to thicker lead titanate superlattices. So we have to go to at least 9 layers of PTO. And here what we find is that, well, we can still use this approach, but the maximum speed that we can reach is much smaller, essentially because the bubbles are much bigger or much more elongated. But still, I think it's remarkable that without making any attempt to optimize these numbers, because we were just trying to prove our concept, we find that the bubbles can be driven at least at 25 meters per second at room temperature. And just to give you a bit of context, the typical or the maximum speed that had been achieved for magnetic skyrmions, which is kind of the magnetic counterpart of everything that I'm showing here, it was of about 100 meters per second until 2 years ago. And well, 2 years ago, this record was clearly broken, and now they can go almost at 1,000 meters per second. But we are for sure, we know that there is much room for improvement in the electric bubble case, because as I told you, that we have made no attempt to optimize these numbers. Okay, and finally, let me show you some results on chirality in bubbles. So first, I want to highlight again that this work has been done by Urmi Maladei, who is a brilliant postdoc working with me at the LIST. Now, a bit of context. Chirality in solid state is a topic that is gaining some momentum nowadays, and it seems like chirality might become a new ferroelectric order like ferroelectricity or ferromagnetism, and this would open, of course, a whole new field. But still, many questions have to be answered for this to happen. So it is quite intriguing, for instance, that there is no unique way to quantify chiral order, nor it is clear how it would be switched or what the associated susceptibilities and conjugate fields would be. Also, to date, very few non-chiral to chiral phase transitions have been predicted in solid-state systems, and moreover, very few among them are mediated by a soft mode. Now, in bubble domains, we know that we can play with epitaxial strain to favor or disfavor the appearance of a Bloch dipole around the domain wall of the bubble. Now, in this way, we can go to a compressive epitaxial regime where the ground state corresponds to a bubble domain with no dipole decorating the wall. So this ground state would be an achiral, so non-chiral state, since it shows mirror planes along x and y. Now, the nice thing is that when we compute the phonon spectrum of this object, what we see is that there is a rather flat and very low frequency optical phonon band, and when we look at the eigenmode at gamma, it looks something like this. So it corresponds to the appearance of a Bloch dipole along all over the domain wall. So this structural distortion actually breaks the remaining mirror symmetries and thus makes the system chiral. Now, the handedness of the chirality is given by the sign of the amplitude of the phonon, and what we can say from this calculation is that this is a structurally chiral phonon mode. So now we can follow the evolution of this chiral mode as a function of epitaxial strain. And what we see is that coming from the very compressive strain regime on the left, the mode softens following essentially a textbook behavior, with the frequency square going linearly all the way down to 0 at the critical strain. Then, when we keep on expanding the system in the plane beyond the critical strain, the chiral mode condenses and the system becomes chiral. So we can also compute curves of energy versus the chiral mode amplitude, and what we see is that now in the tensile regime, the energy shows the characteristic double whale structure of a broken symmetry phase. Now, as we go back to the compressive strain regime, we see how this curve now transforms into a single well corresponding to the non-chiral state. So all in all, I believe that these two figures convey a clear message, which is that electric bubbles display textbook soft mode non-chiral to chiral transition with epitaxial strain. Now, I don't have time to go over all the interesting things that we found, but let me just highlight one very interesting thing, at least in my opinion. So we saw that this chiral mode that I have been describing corresponds to an excitation where the Bloch component along the bubble wall is essentially constant throughout the height or the z direction of the bubble. That is, all along the thickness of the lead titanate layer. So essentially what we had is a picture like this, where the eigenmode essentially has this constant helicity, handedness, all throughout the lead titanate layer. Now what is very interesting is that in all these structures where we found chiral phonons, we also found higher frequency modes where we saw that there was this handedness, there's chirality, but the handedness would change sign as you move through the lead titanate layer, as you move in the z direction. So for instance, here you are seeing a structure with essentially one node of the chirality or the chiral order parameter as you go upwards in the lead titanate layer. And if we keep on analyzing eigenmodes of higher frequency, we also find another structure which shows two nodes of the chiral order. And actually, if you plot essentially the amplitude of this in-plane component of these chiral modes, what we find is that they essentially look very beautifully like the harmonic modes of a resonant cavity. So I guess you could call these things chirality harmonics. And the nodes in which the chirality or the chiral order goes to zero and then changes sign, we propose to call them Ising rings because essentially they correspond to Ising domain walls which have a ring shape. Now for more details, please check out our preprint. Okay, we made it. With this, I come to the final slide with the take-home messages. So first, I told you how electric skyrmion bubbles can behave as new quasiparticles which undergo Brownian motion, and this motion can be thermally activated according to our simulations. Next, I told you how we propose to create currents of these electric skyrmion bubbles by essentially using inhomogeneous fields. And finally, I described our most recent predictions by which electric bubbles display a textbook soft mode chiral phase transition in solid state. Okay, so thank you very much for your attention, and please send me any questions you may have to the address that you see here below. Bye!